I always want to say bad to the bone after that place. Anyway, sorry about that. How's everybody doing? Okay, lesson 3, perms and coms. Today we're looking at permutations with restrictions, but we already have looked at that in lesson 1, really. So we're going to revisit that, but within that we also have, like, that's not only where they restrict where a certain thing can go, what position, but we're also going to look at the togetherness thing, I call it, when they tell you that certain things have to be together. So there's placement and then there's togetherness. Okay, so, and then the second half of this lesson is on repetitions, so we will get to that in a few minutes. All right, so first of all, example 1, we're going to take the letters in the word oranges and we're going to rearrange them. First situation, there's no further restrictions, okay, which means they're not telling you where to put a certain letter or if things have to be together or whatever. So if there's no further restrictions, we can either use the NPR formula, which is great if there's nothing weird going on, which means there would be 1, 2, 3, 4, 5, 6, 7 letters, and we're picking all 7 letters to rearrange. Okay, so let's grab our calculators and figure out what that would be. Now, if you recall, when we put this in the calculator, we'd have to put 7 first, then go math, and then I go to the left to get to PRB, and then we're choosing number 2, and then another 7. So that's 7 pick 7, or 7 NPR 7. Okay, and we hit that, we get 5,040. Okay, so that's one way we could do this particular question. Or we could fall back to fundamental counting principle, which means we have 7 blanks because there's 7 letters to rearrange. We would have 7 choices for the first letter, and then I've used up one of the letters, so 6 choices for the next letter. Used up 2 of the letters, so 5 choices, and you can see where this is going, right? And we learned that that's otherwise known as 7 factorial. Okay, and then we could go to the calculator and figure that out, and we would find out that that's also equal to 5,040. So either one of those ways. Now, the downside with the NPR formula, it really can only be used if there's no restrictions on where things can go and if there's no togetherness thing happening, whatever. So the fallback position, if there is weirdness going on, is fundamental counting principle or that situation. Okay, the first letter must be an N, part B here. So let's fall back to fundamental counting principle. Okay, so we have 7 positions to fill with these 7 letters, but we know the first letter has to be an N. So if that has to be an N, we only have one choice because there's only one N here. And then we've used up the N, so now we have 6 choices left. Now we've used up another letter, so 5, and you can kind of see where this is going, 4, 3, 2, 1. Or if you recognize that right off the bat and you have a lot of letters to deal with, you can just simply write that as 1 times 6 factorial, which would end up equaling 720, I believe. Okay, let's look at part C. The vowels must be together. Okay, so here's the togetherness thing I was talking about. Okay, so one way to look at this is to take the letters O, A, and E and put them in a box, okay? Or in other words, what I call gluing them together. They are now one letter, okay? O, A, E, all one letter. Then we have R still as a letter. We have N as a letter. We have G. And we have S. Okay, so how many letters do we have to rearrange then? We've got 1, 2, 3, 4, 5. Okay, so how many ways to rearrange 5 letters? Well, that would be 5 factorial. Okay, now if they'd said in no particular order for the O, A, and E, we would then rearrange those 3 letters within that group for every situation in which we rearrange the letters. And we'll get to that in a minute. But if it's in that particular order, you glue them together, they stick together, you're done. And your answer 5 factorial would be 120 ways to do that. Okay, in how many arrangements of the letters of the word brains are the vowels together? So vowels, A, E, I, O, and U, and sometimes Y. Don't worry about the Y thing, they'll just avoid using Y in the question probably. Okay, how many arrangements of the letters in the... Okay, so we have A and E are going to be stuck together. but we still have these letters as well. Okay, so if you count how many letters, there's one letter for A and I, and then 2, 3, 4, 5. So again, there's 5 factorial ways to rearrange those 5 letters. However, they did not say the vowels had to be in the order of A and I. So they could have been A and I, or it could have been I and A. So for every situation where you had, A and I, you could also switch them around. So you would actually multiply that by 2, like double it. Now, if there are 3 letters, you would actually have 6 different ways, or in other words, it's really you're multiplying by the factorial of how many letters you are rearranging within that group. Okay, so this is rearrange within the group, rearrange within the glued, I should say, the glued group. Okay, and this is rearrange number of letters, and I'm going to put letters in quotes because really one of those isn't just one letter. But okay, so hopefully we're all clear. You multiply those out, we should get 240. All right, example number 3. Find the number of permutations of the letters in the word kitchen if the okay, 2 situations. The letters K, C, and N must be together, but not necessarily in that order. Okay, I want you to take a stab at what you think this would be. So glue them together if it helps to kind of box them, like go K, C, N, all glued together, and then write down all your other letters. Okay, then go ahead and do that, and we'll check back in a minute. Pause your video. Okay, so once we glued K, C, and N together and then counted the other letters in addition to that, we would have 5 so-called letters. And number of ways to rearrange them, 5 factorial. Within that group, there's 3 letters, so to rearrange the 3 letters within that group, that would actually be 3 factorial ways to do that, and which means we're going 120 times 6, which is 720 permutations of the letters in the word kitchen if K, C, and N are kept together. Okay, let's try the next one. Okay, a little bit trickier here. The vowels must not be together. Okay, that word not kind of messes this question up, I tell you. Okay, you could go forever trying to figure out how many ways to do that. Or one of the ways I find works quite well is if you take the complement event of this, which is really what isn't what they're asking for, and you subtract it from the total. So if you take total number of ways of rearranging all these letters, we don't care what order, okay, minus all the ways in which, so number of ways the vowels were together, you would get all the ways in which the vowels were not together. Okay, so let's see. Okay, total number of ways. We have 1, 2, 3, 4, 5, 6, 7 letters in the word kitchen. Number of ways to rearrange those would be 7 factorial, minus all the ways in which the vowels are together. So we have 2 vowels. So altogether we have 1, 2, 3, 4, 5, 6 letters to rearrange then. 6 letters because I and E are glued together, but within I and E you could switch those around. There's 2 of them, so times 2 factorial. And there we go. So 7 factorial minus 6 factorial times 2 factorial. Okay, we could do that on the calculator. We know 7 factorial is 5040 minus 6 factorial 720 times 2. Okay, and let's grab the calculator and figure out what that is. Okay, so typing that in, we should end up with 3600. Okay, so our answer should be 3600. All right, let's take a look at the next one. How many ways can 3 girls and 4 boys be arranged in a row if no 2 people of the same gender can sit together? Okay, they're throwing a restriction at you here, so I'm just going to fall back to fundamental counting principle here. So we've got 7 people. Okay, and if we're going to have no 2 people of the same gender sit together and there's more boys than girls, we should actually start with a boy then in the first position, then a girl, then a boy, then a girl, then a boy, then a girl, then a boy. Okay, so we've used up 1, 2, 3, 4 boys. Okay, good. So let's figure out now how many choices we have to do that. So first position is going to be a boy. How many choices for boys? Well, we have 4 boys, so there should be 4 choices. Times fundamental counting principle, we're multiplying. Choices for girl, 3. Okay, now boys, we've already used 1 boy in the first position, so we only have 3 left to choose from. Okay, then a girl, I've already used up 1 girl of the 3, so I only have 2 left. Then a boy again, there's only 2 left, and 1 girl left, and 1 boy left. In essence, that is essentially 4 factorial times 3 factorial, but I think it helps to use fundamental counting principle to see that. And if we throw that in our calculator, we will get 144, 4 factorial times 3 factorial. Okay, so 144. Awesome. Okay, example number 5. 6 actors and 6 actors and 8 actresses are available for play with 4 male roles and 3 female roles. How many different cast lists are possible? Well, this one actually lends itself well to the NPR formula. It's permutation because the roles have different characteristics, right? So if we're trying to fill those 4 male roles from using 6 actors, we would have, this is assuming you can't cross over, right? Okay, so 6, and we are filling them with, I'm not even going to try and erase it, it's probably going to hang up on me. So 6 pick, and we have to pick 4 of those actors to fill those 4 male roles. And then we have to choose the actresses. So we have 8 actresses, and we want to pick 3 of them to fill the 3 female roles. Now the question is, would we add these 2 permutation formulas together or multiply them? So say it in your head. Am I filling 4 male roles or 3 female roles, or am I filling 4 male roles and 3 female roles? And what works better? Yes, the word and. So the word and in this unit means multiply, and or is add. Okay, so if we do that, we should end up with, let's go to the calculators. Okay, big number, 120,960. Now, if you'll note what I put into the calculator here, you do not need to put brackets around the 6 pick 4 or the 8 pick 3 because it's a function and the calculator will do that first before it does multiplying. Okay, so we have 120,960 as our answer. Okay, great job. Let's take a look at the next page where we investigate repetitions. Okay, so if we have, for instance, in a word like the word rose, okay, number of ways to rearrange all the letters in that word would be there's 4 letters, so 4 factorial, which is 24, or you could do 4 pick 4. Okay, and they've kind of written them all out here, and you'll see why in a minute. Okay, so those are all the different 24 arrangements. Now, they're saying, what if we changed, say, the E to an S, and we get the word Ross, okay? Every time, so they did that in these first 2 letters, right? So these 2, even though originally were 2 different permutations, these 2 really look identical. So you can't consider this one or one of those to be a unique permutation. So we would have to actually get rid of that one. And same thing here, RSOS, RSOS. Okay, so if you go through and you cross out all the ones that look identical and just keep one of the ones to represent, you would end up with 12 different arrangements. Okay, now let's see how that compares. Well, if we take our original number of permutations, 4 factorial, and we divide by 2, 24 divided by 2, we get 12. Okay, let's try changing another letter to an S. And here are all our different permutations. Okay, and when we cross out all the ones that are similar, we only end up with 4 different arrangements. Okay, which would be the same thing as going 4 factorial divided by 3 factorial to get 4. So, in other words, the conclusion is, if a letter appears more than once in a word, you're going to divide by how many times it appears factorial, and then you'll get the number of unique permutations. All right, so we're going to try some examples with that and take a look at the formula then in part 2 of lesson 3, and we we will see you then.